Hello everyone, this is Nick Tuzov. Today is part 2 of my tutorial for Causal Fusion, a powerful causal inference tool created by Professor Bareinboim and his team. In part 1 we covered the basics, how to create directed acyclic graphs, and in this video we are going to cover identification of interventions and some elements of causal discovery. I'm going to assume that you have some introductory background in causal inference from the sources such as the Book of Y and Causal Inference Primer. In terms of Causal Fusion interface, we are going to cover most of the items in this right panel menu. Confounding Analysis, Path Analysis, and calculus belongs to causal identification, and testable implications belong to causal discovery. We are not doing any counterfactuals or estimation, even though it's possible to run estimation within Causal Fusion. So as you can see, I already created a graph here. All of the nodes are of this type. In terms of Causal Inference Primer, they are endogenous and observable variables. In order to identify our interventional causal query, we have to label the treatment and outcome first, and for that we go to this summary and type in treatment and outcome that get highlighted with blue and red respectively. For this DAG, it's fairly clear that backdoor, front door, and instrumental variable approaches are all applicable. So let's see how we can get them through Causal Fusion using this confounding analysis menu that has 6 submenus. They are essentially grouped in pairs. The first 2 submenus apply to the backdoor, the next 2 to the instrumental variable approach, and the last 2 to front door method. So when we click on admissible sets here, we immediately get all of the sets that we can use for adjustment in our backdoor estimand. C1, C2 works, or you can adjust for C2 and C3 because clearly either of these sets blocks all of the backdoor paths from X to Y. If you want to check your own admissibility set, you can use the next menu item and type in your set. As you can see, adjusting just for C1 in the backdoor approach doesn't work, because as we see from this explanation, C1 by itself doesn't block every path from X to Y that contains an arrow into X. In particular X, C2, Y remains open. But if we add C2, then it starts working. Sometimes in some simple cases you are lucky and you don't need any adjustment, in which case you should check whether an empty set is admissible for the backdoor. Apparently for this graph it's not admissible, but if we delete a couple of edges, then it becomes admissible. And in this case, the interventional distribution of y given that we apply the do operator to x is the same as a regular conditional distribution of y given x that you can compute from the observational data. Now let's look if we have any instrumental variables. As you can see, this menu item gives us a full list. It was clear from the beginning that Z1 and Z2 are instruments, but it turns out that C1, if adjusted for C3, is also an instrument. Similarly to the previous example, if you want to test your own ideas for instruments, you can do it here. In particular, C1 by itself is not an instrument. And the explanation tells us that this disseparation condition doesn't hold. But if we go and adjust C1 for C3, then it becomes an instrument as expected. Now let's look at the front door approach. So we immediately get that we can apply front door by adjusting for M1 and M2, these two mediators. And if we want to test our own ideas for other admissible sets, we can do it here. In particular, M1 by itself is not admissible because M1 doesn't intercept all causal paths from X to Y, because there is this X M2Y path. But if we add M2, then M1, M2 becomes admissible as expected. Okay, now let's take our graph and make some of the nodes latent, unobserved. It's fairly clear that for this graph, the backdoor and front door are no longer available. So let's check whether it's the case using the confounding analysis. So, as expected, for the backdoor, there are no admissible sets. For the front door, there are no admissible sets. If we try to run the front door with just M1, it's not going to work because M1 doesn't intercept all causal paths from X to Y, as we see from the explanation. At the same time, it's fairly clear that IV should still work, and as we see here, Z1 and Z2 are still valid instruments, and we can run it with Z1, for instance. All of the conditions hold except the parametric assumptions of the instrumental variable approach are not listed here. As you know, we are forced to assume a linear relationship between Z and X and between X and Y in order to be able to apply instrumental variables. So as you can see, confounding analysis is a great tool that resolves the issue of identification of interventional queries in a more or less automatic manner. Okay, now that we know that we have three distinct estimands for this graph, let's try to get them in symbolic form. So I just click this compute button and I get a familiar formula for the backdoor estimand, where the adjustment set is C1 and C2. I don't know how to request the formula for the other admissible set. If there is a way, I didn't find it. So we just get 1 out of 2. Now, if you click on derivation, you are going to get this detailed derivation using the SCM and do calculus approach. But if you like potential outcomes better, you can switch to derivation using the potential outcomes framework. They are mathematically equivalent. You can also download your derivation in LaTeX, PDF, or both. Now, what can we do next? And there is another button here that switches between linear assumptions and a non-parametric case. So we can click on turn on the linearity and compute it again. And here we get our backdoor estimand in terms of covariances. Now, to get the front door sets, front door estimand, even though it's identified, I didn't find a way to request it, so it just seems that when the backdoor is available, it takes precedence over all the other estimands, if any. Therefore, in order to enable the formula for the front door, I'm going to make C1 and C2 latent. Then, if I click compute, again, you will see this fairly familiar formula for the front door that you can recognize by this double summation / integration operation. As you can see, our instrumental variables are available, but again, it appears like when the front door is identified, it takes precedence over the IV when you click compute. So I'm going to see it by making these three nodes latent. Now you can see that the back door is gone, the front door is gone, and the only thing I can count on is the instrumental variable approach. I click compute and we get that the interventional distribution of y given to x is not identifiable. And that is apparently because we do not assume linearity. So if I switch to linear mode and compute it again, I will get the estimand in terms of covariances. Again, note that even though I have two instrumental variables, the estimand uses only one. And I don't know how to enable to specify that I want a specific instrument or a set of instrumental variables. In the previous cases, those cases were fairly textbook, and it was fairly easy to tell what is identified by just eyeballing the graph. So this time I decided to make it more interesting and add a couple of the so-called variance reducers. As you can see, D1 and D2 explain some of the variation in the response, and at the same time, D1 and D2 are not associated with the treatment or confounders. So it's fairly clear that we can reduce the variance of our estimator, or at least we have to try, by including D1 and D2 in our estimand. As you can see here we have front door identified and IV. So when I click on compute, it should produce the front door estimand. Let's see if D1, D2 or both are going to be included in its right-hand side. So as you can see, we get the old estimand that doesn't include D1 and D2. Now, let's try linear assumptions. And this time we see that indeed, in the right-hand side, we see D1. If I'm not mistaken, correct me if I'm wrong, but I believe it should be possible to produce a similar estimand in non-parametric form in terms of conditional probabilities, just like this one. But that feature is not implemented. Another thing is that D1 and D2 are completely symmetrical in the sense that I can replace D1 with D2 and the formula is going to be valid, but for some reason only one out of two variance reducers is included. So let's remove this edge and recompute it. And as you can see now, D2 is included because I forced it to be included by excluding D1 by hand. So in general, we can see that Causal Fusion can give us valuable clues as to variance reducers, but we have to do a good amount of manual work by playing with it and hacking like I did here. And it's not going to give us a full list of variance reducers the way it is done with respect to instrumental variables here. Let's look at path analysis menu, where the very first item is d-separation. It's a regular test for d-separation where we try to test our hypothesis about whether two sets of nodes are d-separated given another set. So as you can see here, Z1 and Z2 are d-separated by default because all of the paths between Z1 and Z2 go through this treatment X that is a collider with respect to all of those paths. However, as expected, if we condition on the collider, we get that Z1 and Z2 become deconnected. Now let's try to deseparate x and y. Apparently we have to block these two chains that pass through the two mediators. So here I included M1 and M2. And also we need to block the backdoor paths. So apparently we'll need C2 and maybe C1. If we don't like C1, we can block this backdoor path x1 C3y by replacing C1 with C3. Now let's look at causal paths functionality. Let's turn it on. And as you can see, there is a spin button here and the causal paths are shown in green. If I click more, I can increase the max number of paths shown, but in my case, there are only two causal paths between treatment and outcome, so I'll be just cycling between these two. Next, the Confounding Paths button works in a similar manner. Confounding paths are shown in red. Can I get more? So in this case, the more button doesn't work the same way as here for some reason. Okay, now let's look at the biasing path submenu. As far as I know, biasing path by definition is any open non-causal path between treatment and outcome. Confounding path is a subset of biasing paths. It's an open non-causal path that is open due to the presence of some variable like C1 and C2 here that is a common cause of treatment and outcome. To give you an example from the book on Y, in the Simpson's paradox and in the Bergson paradox, in either case there is an open non-causal path between treatment and outcome. Only in Simpson's case it's a confounding path, and in the Bergson paradox that path is not of a confounding type, but it's due to the collider bias. So for this graph, in order to create an open non-causal path that is not of confounding type, I have to create a collider whose parents are treatment and outcome and condition on that collider. So I cannot condition on a regular node like C1, and I believe there is a special type of node in Causal Fusion for that that's called selection bias, because selection bias is a particular case of collider bias. So that's what I did. I added this node S, selection bias node, and connected X and Y to it. However, when I use this biasing path box here, it cycles me through the two confounding paths that go through C1 and C2, and that in this case are highlighted with light brown, but it doesn't highlight the path that is open because this collider is conditioned on. That is the path X, S, Y. In order to check it again, I loaded this DAG from the paper of Bareinboim and Pearl 2016, an example of selection bias. And here we get that there are no confounding paths, which is true because this path is not of confounding type. But there are no any biasing paths at all. So, which appears to be a bug because this path has to be highlighted through this functionality. Okay, now let's look at do calculus analysis, and we'll start with do separation. When you click, you'll see this interface, and it's identical to what you see when you click on this button that is called do calculus inspector, and therefore I think it's a small inconsistency here because this button should have been called do separation also. Technically, do separation is like regular deseparation. For instance, Suppose that we want to see if x and y are d-separated given m1 and m2. Apparently they are not, but in this do separation there is an extra condition that you can specify in this box. So if we place C3 in this first box here, then in the graph all of the edges pointing to C3 are going to be removed. If we place, say, C2 in this box, then in the graph all of the edges pointing out of C2 are going to be removed. And therefore, under this condition, x and y are indeed separated given that we adjust for m1 and m2. The act of removing these edges from the graph is called graph mutilation or graph surgery, and that's probably why this icon here looks like a surgical scalpel. Now this do separation functionality is used not in isolation but in the context of the rules of do calculus. Every rule has a condition under which the rule can be applied, and this is essentially a general form which we can use to check that condition. Generally, it sounds like if a certain d-separation takes place in the mutilated bag, that's mutilated in a certain way, then it's possible to transform the probabilistic expression for our query in a way that eventually it's free of the do operators. To see exactly what I mean, let's actually switch to the theoretical definition of the three rules of the do calculus for interventions. This is from the book of Professor Bareinboim. I'll add the link in the video description, and it's free. So, for instance, let's take rule number 2 that holds under this condition. As you can see, this condition is where you need to check a certain d-separation in this graph capital G with a lower subscript x bar and z underscore. So x bar means that the graph should be mutilated so that all of the edges pointing into x are removed. And z underscore means that all of the edges pointing out of z should be removed also. If we switch to Causal Fusion interface, you will notice that in this, here we also have letter G, and these two boxes have bars, the top bar and the underscore. So if we print x here and z here, and that will mean exactly the same thing, the same rule for mutilation as specified in this mutilated graph that's used in rule number 2. Let's see how we can match the interface, so to speak, of this rule number 2 to the interface of Causal Fusion. In Causal Fusion, we have to specify 4 variables or sets of variables, x, y, z, and w. Then we have to specify this separating condition and the graph mutilation. In terms of Causal Fusion, we can do it in 2 ways. First, by using this do separation tool, in which case the boxes are populated as follows. This is x bar, this is z underscore, and we check for the separation of y and z given x and w. I took these in parentheses because apparently for your specific graph, the 4 variables should be expressed with your actual variables names like a, b, or c. Another more convenient way to apply rule number 2 is to use the do calculus inspector, select rule number 2, and populate these 4 boxes as follows. In practice, your w and z can be empty, but treatment and outcome should always be specified. Also, do not take these labels such as treatment and outcome literally. For instance, in this example of this graph, it doesn't mean that outcome should always be populated with node C. If you look at the theorem, it says that x, y, z, w can be any disjoint sets. You will see what I mean from the following example. Now, doCalculus Inspector is more convenient to use than this tool for two reasons. First of all, you don't need to specify a graph mutilation. In this example, once you specify x and z, this mutilation will be applied in the doCalculus Inspector automatically. Number two, the system will actually apply the rule and produce the result for you. Now let's see how doCalculus works on a specific example. Here we have a most simple confounding case for which we have the backdoor. And as you will see in a second, derivation suggests that we can apply rule number 3 and then rule number 2. Let's double check the derivation by applying these two rules by hand in Causal Fusion. I'll skip directly to the derivation of the backdoor estimand, and we are going to start with step 4 because the previous steps are not related to causal calculus. So here we have this term, the probability of B given do A and do C. When we click here, we see the mutilating graph. From this expression, we get that all the nodes pointing out of A and C should be removed, which leaves no edges. As a result, this separation is trivial, and of course it holds. In order to check it manually, we can go up where I already populated the mutilation condition, the separation, and as you can see, the sets are deseparated, meaning that rule number 3 applies. Now, if we go to the do inspector here, we have to populate these 4 boxes, which is slightly confusing because, as you can see here, in the treatment, instead of just A, I put both A and C. And outcome is B, even though in the original graph outcome is C. So the reason I did that is because if we go and look at the term that we want to simplify, here B is on the left-hand side of the conditional bar, and if we compare this to our rule number 3, it's clear that B should match to Y. So, and our W and our Z are empty in this case. After we populate these 4 inputs, the do inspector automatically applies the corresponding mutilation, whereas here we had to do it manually, and that mutilation will match this expression that depends on X, Z, and W. As a result, we get that rule 3 is applicable, and just like in the derivation, we get that these two do operators can be dropped altogether, and our expression simplifies just to the probability of B. Let's go back to derivation and apply rule number 2. Here, we have to check this separation in this mutilated graph where all the edges pointing out of A and B are removed. Again, we get that after mutilation there are no edges, and apparently the rule is applicable. In this interface, we can specify it as follows. We get deseparation, and again, confirm that the rule is applicable. In this case, in do inspector, we have to specify X, Y, W, and Z, and in this case, it's clear that what the formula in the book means by Y is C, and what it means by X is A and B. Here's the original formula. And therefore, after we populate this, rule 2 is applicable, and as you can see, we can replace the two do operators with regular conditional, just like in the derivation. Now let's talk a bit about causal discovery and how to do it in Causal Fusion. Up to this point, we assume that our directed acyclic graph actually corresponds to the true data generating process, but we never used the dataset to check whether it's the case. Our graph is essentially a statistical hypothesis, and any good hypothesis has to be falsifiable. It means that we can never quote-unquote prove that our hypothesis is true, but we should be able to set up some experiments that can potentially refute the hypothesis and demonstrate that it is false if the hypothesis is at odds with the data. In causal inference, refutation is done by using the testable implications implied by the DAG, and in Causal Fusion, all of the testable implications are found in testable implications menu. The first submenu is conditional independencies implied by the DAG. For instance, given x, C1 should be conditionally independent of M1. This menu is related to path analysis deseparation, where you can manually check whether this separation/independence takes place. In order to test your implications versus the real dataset, you will have to assume a certain form of functional relationship among your variables in your DAG. For instance, to test this particular implication, consider the simplest case when C1, M1, and X are all quantitative, and on top of that, we assume that the relationship is linear. Then, to try to refute that implication, we can do the following thing. Using a linear regression from any statistical package, regress C1 on M1 and X. Then look at the p-value for M1. That p-value, the so-called type 3 p-value, describes how useful M1 is in explaining the variance of C1, given that X is already in the model. If the p-value is high, we can interpret it as not having enough evidence to refute this implication. Needless to say, you are not limited to linear regression, and you can use logistic regression, classification and regression trees, GBM, and state-of-the-art methods such as deep learning methods. In some of these methods, you're not going to see any p-values or any variable importance measures for that matter, but you can reformulate this implication in terms of predictions. In this example, you can say that let me fit two models. The first model predicts C1 using just X, and model 2 predicts C1 using both M1 and X. If the quality of prediction doesn't differ much between the two models, we can interpret that as evidence that once X as a predictor is already in the model, the predictor M1 is redundant. And again, we can say that in that sense, we don't have enough evidence to refute this implication. I don't know if Causal Fusion contains a functionality that allows one to automate the testing of all of the conditional independencies using a specific dataset. Even if yes, I don't want to cover it today. However, even if it's possible, and it may be possible in other packages also, I want to make a remark that you should take the output of such automated testing with a grain of salt. Consider the simplest case when all of the variables here are quantitative and we assume that all of the relationships are linear. The package will run a bunch of multiple linear regressions and report the respective p-values. But if you took statistics, you know that p-values can be very sensitive to the violation of linear regression assumptions. For instance, in this case, the p-value for M1 can be reported as 40%, but if we remove a single outlier from the dataset, it can be changed to a very small value, and the p-value can become 10 to the power minus 10 or so. Therefore, those who automate the testing of implications will be forced to sweep under the carpet a lot of details. And while it can appear to be a useful tool, you really cannot take its output at face value. So if I were serious about refuting the DAG, what I would do is to use Causal Fusion to extract conditional independencies in symbolic form, like these, and then use a separate computational package to fit the models and test the implications where I myself can control what models are used and how they are used, in particular whether the assumptions that underlie those models are satisfied, to make sure that my inference is not affected by one or two outliers, among other things. I'll show you an example of that kind in the next section. In this section, I'm going to introduce Verma constraints, and I will show you how to test a Verma constraint outside of Fusion using a third-party package in order to have full control of the model that is used for the testing to make sure that your test results are more or less valid. I took this graph from the book of Dr. Robert Ness called Causal Artificial Intelligence, section 4.5. However, it should be familiar to you from the book of Y and Causal Primer also. That's our classic smoking study where we try to find a causal relationship between smoking and lung cancer. Back in the day, some distinguished individuals argued that maybe there is no causal relationship between smoking and lung cancer because there is this genetic predisposition that is a common cause of two things. Number one, craving for nicotine. Number two, propensity for lung cancer. When we go to conditional independencies for this graph, we see that we have 5 independencies we can use to refute the graph. But what if this cancer gene factor is latent? In that case, we lose 4 out of 5 of the conditional independencies, but what we get instead is one Verma constraint. A Verma constraint is like a regular conditional independence, only it has a more complex form because it's expressed in terms of functions of observed variables. So here on the left-hand side we have this function expressed in non-parametric form. And the next step would be to estimate these two probabilities from the actual dataset, and then somehow test the hypothesis that this left-hand side is independent of the right-hand side, which is just the cigarette cost. Next, we are going to switch to Python code and see how exactly these two probabilities are estimated, and how the left-hand side of the Verma constraint is estimated for every observation, and finally how exactly we test this constraint to obtain the p-value for the null hypothesis that the left-hand side is independent of the right-hand side. This is the GitHub for the book of Robert Ness that's publicly available, even though the book itself is not free. I'm gonna give you all the links in the video description. In short, Robert Ness used some Bayes classifiers to compute these two probabilities. See, they are both computed by using some naive Bayes classifiers in Python. Then he computed the function h, it's the same as the left-hand side of the Verma constraint, and he plotted that left-hand side versus c for every level of c. So as we can see here, it doesn't appear to be much of a relationship between h and c. In order to test it formally, he used the standard analysis of variance, where h, or the left-hand side of the Verma constraint, is the continuous response, and c, the right-hand side of the Verma constraint, is a factor with 3 levels. There is some Python code here, and as a result, we get this model p-value of 18% that gives us ground to say that we don't have enough evidence to refute the Verma constraint, and it stands. In this case, there was no additional diagnostics and sensitivity checks run for this model, but we can see that as a sanity check, it's perfectly fine. There are no crazy outliers. We don't have a situation when, for some level of C, we only have a couple of observations, etc. Incidentally, a statistician like myself could try to split hairs and argue that there is a second-order dependence between this random function h, the left-hand side of Verma constraint, and the variable c, because it appears that the variance of h is dependent on c. Here, for the medium level, the variance appears to be much smaller than for the low level of c. But that kind of reasoning is beyond a simple sanity check, and as a sanity check, this method is perfectly fine. Now, consider what happens when you decide to save time and apply an automated approach to verifying the testable implications. In the book of Robert Ness, that approach is called Commodification of Inference. Suppose you have 10 implications. Then your package will run a similar code for each of the 10 cases and generate the p-value. Because you have 10 tests, to get the final answer, a multiple testing correction is necessary that can also be done automatically, for instance by applying Bonferroni or Benjamini-Hochberg correction. And finally, you'll get your final answer for the null hypothesis as to whether your DAG is consistent with your dataset as a whole. There is a chance that in at least 1 out of 10 cases, the analysis of variance assumptions may be violated, and the p-value you got automatically is completely inadequate. Because the final answer depends on all of the p-values, that p-value will affect your final conclusion as well. But if you commodify the inference, you are not going to learn of any of those issues because by necessity they are all swept under the carpet for the sake of speed and convenience. On the other hand, what if your DAG is much bigger and you have not 1, 2, or 10, but say 500 testable implications? In that case, running a more or less valid sanity check like in this example by hand 500 times in a row is indeed way too time-consuming, and it appears that you don't have a choice but to commodify and automate that refutation step. Therefore, the commodification of inference may be unavoidable in some cases, but still you have to keep in mind that there is a trade-off between the speed and the quality of your statistical analysis. Okay, let's switch back to Causal Fusion and consider one more corner case with respect to the testable implications. As you can see, for this DAG, we have 2 testable implications, but what if we remove this node cigarette cost? In that case, we will get this DAG, and you should recognize it from the introductory books as the standard way to introduce the front door estimation. Indeed, if we click on the compute button, we'll see that the front door estimand is available, and we can use our dataset to obtain the specific value of that causal effect. On the other hand, in testable implications, there is not a single conditional independence or Verma constraint, meaning that for any dataset represented by these 3 observed variables, there is no way to refute our directed acyclic graph. There is no way to check whether this assumed structure is consistent with the data. Therefore, we get this weird situation when, on the one hand, the causal effect is identified and we can produce a specific estimate for it for any given dataset, but our analysis is based on the hypothesis that is represented by this DAG, and that hypothesis is not falsifiable in principle. Well, this is the end of our second tutorial. Given that as of October 2025 there is still no official Causal Fusion documentation, and the fact that we covered a lot of functionality today, I believe the video contains some errors, and I urge you to point them out in the comments below. I do hope that before long the Causal Fusion team issues some official documentation, especially for the areas that I haven't covered, such as estimation. Please check out the relevant links in the video description. And if you are into Causal Inference, please find me and connect with me on LinkedIn. Thank you for watching.